My name is Shreyas Basavathiya, and this is my Lab 2 report. So, as an introduction, the purpose of this lab was to observe and understand the motion of an object that was falling down vertically, and then to generate a computational model to model the motion of this object, and use these models to determine the forces acting on the falling objects. We create two computational models, one that uses only the force of gravity on the object, and one with both the force of gravity and the drag force. So some physics principles that are associated with this lab are Newton's second law, or this momentum principle, which you can see in the bottom right corner. This shows us the velocity update formula and the position update formula, which we use for the computational models to predict the motion of the object. Also, this principle relates the net force along with to the acceleration of the object. We also explore the gravitational force, which the equation is shown as F equals big G times m1 and 2 over the distance squared. The gravitational force acts on the object that is falling vertically, and so we experience its effects in this lab. In addition, the object experiences the drag force, which equation is shown as to be F equals negative B times V squared. We examine the effects of the drag force in this lab as well. And so as preliminary results, we find that the computational model that includes drag force and the gravitational force is more accurate than the computational model with just the gravitational force in predicting the motion of the falling object. So for the actual experiment, I dropped a piece of crumpled paper vertically. So the system was the paper ball, and the surroundings that acted on the paper ball were the earth and my hand as I dropped the object. Some of the initial conditions include that the hand holds the paper ball at the top of the frame of the video, and does not push the ball, but simply lets go when the video starts, and tracking starts once the hand lets go of the ball. This video was then put into Tracker, and I first used a calibration stick to show Tracker how large the ball was in real life and gave it a measurement. I then tracked the position of the ball's movement each frame, clicking on the location of the ball as each frame went along. So some sources of error here are unsteady video. So the video was not perfectly steady as someone was holding the camera and it moved a small bit. So small discrepancies between where the tracker thinks the object is and where it actually is might occur. In addition, there's some inconsistent tracking with each frame, as it's hard to click the same exact region of the ball for each and every frame. That's just a source of human error. So for the computational model, I utilized the provided starter code and made some small changes that reflected the data I gathered. So first I set delta t to be equal to 0.33 seconds because that was the frame rate of the video that I took. The total recording length was set to 0.567 seconds, so the loop only ran for that long. Then the net force was set to the force of gravity plus the drag force. I made two computational models, one that only included gravity and one that included both the gravity and the drag force. And finally, I changed the velocity and position update formulas to reflect this by multiplying the values by delta time. So I found when I plotted out the results, we can see that the actual tracking of the object is shown in blue, the computational model number 2, which included both the drag force and the gravitational force, is shown in green, and the computational model 1, which shows just the gravitational force, is in orange. As you can see, the computational model that includes drag and the gravitational force reflects the actual motion of the object much better, as the lines are closer to each other than the computational model with just gravity. This shows that there likely is a drag force acting upon the object as it's falling, and therefore it's a more accurate model to include the drag force than to not include it. So what if the object was thrown downward instead of starting from rest? Well, the terminal velocity of the object would stay the same, but the terminal velocity would be reached quicker, as the object would have to undergo less acceleration to reach its terminal velocity. And you can see a graph of what this might look like below. And what does this mean? Terminal velocity occurs when the drag force and the gravitational force cancel out, indicating that there is no net force. This leads to a constant negative velocity, so the slope of the velocity time graph is constant, and you can see an example of what this might look like underneath. Thank you for listening.